A doubly circular linked list, DCLL, is an advanced linked list structure in which every node has three components: a data field, a pointer to the next node, and a pointer to the previous node. And unlike a regular doubly linked list, the last node does not point to null. Instead, its next pointer points back to the first node, and the first node's previous pointer points back to the last node, forming a perfectly circular, bidirectional chain of nodes. This structure allows traversal in both forward and backward directions without ever encountering null, making the list suitable for applications requiring continuous looping, bidirectional navigation, or repeated cycling through data. A DCLL begins with a head pointer that references the first node, and optionally a tail pointer is used for faster insertion at the end of the list. Traversing the list from head onward involves following the next pointers until the head is reached again, while backward traversal is done using the previous pointers. A DCLL supports dynamic memory allocation, meaning nodes can be created and removed at runtime without requiring contiguous memory blocks, giving it flexibility over arrays and static structures. Insertion in a doubly circular linked list can be performed at the beginning, at the end, or at any specific position. To insert at the beginning, a new node is created. Its next pointer is set to the current head. Its previous pointer is set to the last node. The last node's next pointer is updated to the new node, and the head's previous pointer is set to the new node. Finally, head is updated to this new node. Insertion at the end involves a similar process but with pointers adjusted around the current last node. Inserting at a specific position requires traversing the list to the desired location and then adjusting both previous and next pointers of surrounding nodes to accommodate the new node. Deletion in a DCLL must maintain the circular and bidirectional structure. Deleting the first node requires moving head to the next node, linking the last node to the new head, and updating head's previous pointer. Deleting the last node requires updating the second last node's next pointer to head and head's previous pointer to the new last node. Deleting at a specific position follows the same principles as insertion, where the previous node's next pointer and the next node's previous pointer are adjusted to skip over the removed node. Since the list has no null pointers, special care must be taken when deleting the only node in the list. In such a case, both head and tail, if used, must be set to null to indicate the list is empty. Searching for an element involves traversing nodes one by one either forward or backward until the element is found or the traversal returns to head, indicating the element is not present. The circular nature makes searching efficient in cyclic applications. But in general, DCLL search operations still take linear time. Updating a node involves locating the node through search and then modifying its data field. The doubly circular linked list offers several advantages over singly circular lists and normal doubly linked lists, because it supports two-way traversal. Moving to previous nodes becomes easy and efficient without needing additional structures or reverse traversal logic. This property makes DCLL ideal for implementing complex data systems such as music playlists, undo-redo systems, image viewers, navigation systems, and round-robin scheduling in operating systems. Since the list is circular, there is no natural endpoint, making repeated looping seamless and efficient. The list cycles automatically without requiring special conditions. Additionally, operations like insertion or deletion at the beginning or end are more efficient because no shifting of elements is required. Unlike arrays, Dynamic memory allocation allows the list to grow or shrink according to need, making it suitable for real-time systems or applications working with unpredictable data sizes. Maintaining previous pointers also simplifies many operations such as reversing the list, merging lists, or swapping nodes. Despite these advantages, the doubly circular linked list has disadvantages, because each node stores 2 pointers instead of 1. It requires more memory than singly circular lists. Pointer manipulation is more complex due to the need to maintain both next and previous pointers correctly, and a small mistake can break the circular structure or produce logical errors such as infinite loops. Debugging is more difficult because the list has no null pointers to indicate starting or ending boundaries. Searching for an element takes O(n) time because every node must be checked sequentially in memory-constrained environments. The overhead of maintaining 2 pointers per node may not be ideal. Implementing DCLL is also more complex due to the numerous special cases that must be handled carefully, such as inserting into an empty list, deleting from a list with only one node, updating head and tail pointers properly, and ensuring that circular links remain intact. Freeing memory during deletion requires careful handling to avoid memory leaks, especially when using malloc and free in C. However, with proper implementation, DCLL becomes one of the most powerful and versatile linked list structures because it combines the benefits of dynamic memory allocation, two-way traversal, and circular looping. Its applications are widespread. Operating systems use circular doubly linked lists to implement process scheduling algorithms, where processes move in forward and backward directions depending on priority and time quantum. Media players use DCLL for continuous playlist looping, allowing users to move to the previous or next song effortlessly. Image viewers use DCLL to navigate indefinitely through pictures, supporting both forward and backward browsing. Simulation systems, robot path controllers, and real-time monitoring tools use circular lists to cycle through data repeatedly without restarting from the beginning. Gaming systems use circular linked lists for maintaining turn orders in multiplayer games. Undo-redo stacks in applications like text editors or graphic tools often use DCLL to maintain bidirectional transitions between states. In summary, a doubly circular linked list is a highly effective data structure that enhances the capabilities of linked lists by providing circular connectivity and bidirectional traversal, though it requires careful handling of pointers and uses more memory than simpler lists. Its flexibility, efficiency in circular applications, and ability to traverse in both directions make it an indispensable structure in software development, operating systems, and real-time applications. With proper understanding and careful implementation, the doubly circular linked list becomes a powerful tool for designing efficient, dynamic, and cyclic data handling systems.